Welcome to this explainer. Today we're taking the abstract physics of p-n junctions and turning them into a concrete, completely practical understanding of the diode. If you've ever wondered exactly how modern electronics manage the absolute chaos of electrical flow, well, you're in the right place. We're going to look really closely at the ultimate one-way traffic cop for electrons. Okay, here's our roadmap for today. First, we'll meet the diode. Then we'll unpack the push and pull of forward and reverse bias, graph that behavior out, and finally, look at how engineers actually model these components in the real world. Let's jump in. Part 1. Meet the diode, the one-way valve. So, at its very core, a diode acts as a strict one-way valve for your circuits. Imagine a water pipe, right? The water can only flow freely in a single direction. If it tries to reverse, bam, a physical flap slams shut. A diode does exactly this just for electricity. And this simple little capability, it's literally what makes things like converting AC power from your wall into the DC power your laptop needs entirely possible. It's a total game changer. Physically, this valve is made of two halves. We've got a p-doped region called the anode and an n-doped region called the cathode, and they're separated by this really vital depletion region right in the middle. Now, when we draw this in a circuit diagram, we use this arrow symbol. It's super intuitive. The arrow points in the direction of conventional current flow, so from anode to cathode, while that vertical line at the tip, it perfectly symbolizes the blocking action in the reverse direction, like a literal wall. Moving on to section 2, forward and reverse bias, the push and pull. To put it simply, biasing is just how we apply a DC voltage across the diode to either open or close our electrical valve. Forward bias imparts enough energy to push electrons right through the junction, effectively turning the valve on. Reverse bias, on the other hand, acts as a total block to prevent current, shutting the valve off. But, what's actually happening to the silicon inside when we do this? Well, there's this fascinating internal tug-of-war happening here. In forward bias, the external voltage repels free electrons, shrinking that depletion region and giving them enough energy to cross over. Boom. Current flows. But if we flip the voltage into reverse bias, we essentially pull those electrons away from the junction. That depletion region widens into a massive barrier, and the valve firmly, completely shuts. All right, part 3, graphing diode behavior and the VI characteristic. Before a typical silicon diode can actually conduct, it has to overcome the barrier potential, which usually sits right around 0.7 volts. You can kind of think of this as an energy hill, or maybe a toll booth. Until your circuit provides at least 0.7 volts of push, your one-way valve isn't going to budge an inch. And when we map this out, you can clearly see that energy hill in action. In forward bias, the current stays practically at zero until we hit that magic 0.7 volt knee. Once we cross that, the current just skyrockets. Conversely, look at the reverse bias side. The current flatlines at zero. The valve is completely blocked. But notice how that graph eventually drops off sharply on the far left side? You definitely want to avoid pushing the reverse voltage too far into what we call reverse breakdown. If you pull on those electrons hard enough with a massive reverse voltage, they'll violently tear right through the junction. And unless that current is strictly limited, the resulting heat will permanently melt your diode into a piece of useless slag. No coming back from that. Let's head into section 4, engineering diode models, from theory to practice. So how do we actually abstract all this complex physics into tools we can use? Well, engineers rely on a hierarchy of models. We've got the ideal model, the practical model, and the complete model. And you basically pick one depending on how much precision your specific task actually requires. For a quick back-of-the-napkin troubleshooting session, we use the ideal model. This treats the diode as a perfect frictionless switch, just on or off. But for actual circuit design, we really need the practical model. By factoring in that 0.7 volt drop, which we represent here as a tiny opposing battery, we account for that barrier potential. I mean, if you're designing a delicate 5-volt power supply, ignoring a 0.7 volt tax would completely ruin your entire circuit. Finally, for ultimate real-world accuracy, we have the complete model. This one actually includes the dynamic resistance of the silicone itself. And hey, that's exactly why our earlier graph had a slight slope to it rather than just going straight vertical. But because the math here gets incredibly tedious and complex, you'll generally leave this complete model to your computer simulation software. Let the machine do the heavy lifting, right? So as we wrap up this explainer, I want you to consider your own projects. Are you doing a quick diagnostic check where a simple ideal switch model is enough? Or are you designing a delicate, low-voltage circuit where that practical 0.7-volt drop makes all the difference in the world? Based on the exact precision you need, which level of diode approximation is going to become your go-to tool? Think about it. Thanks so much for tuning in, and keep experimenting with those circuits.